Okay, so one of the things that can cause you issue in a piecewise function, see this border value is at 4. So do you see here this notation? See how it has the little negative? That means that we are coming in from the left, okay? So what I want to talk about with this example, this is an old question from one of the final exams from a long time ago. If you're coming in from the left, this is going to give you information if you do the limit as x approaches 4 from the left. This one's going to give you the limit as x approaches 4 to the right. And see how this is equal to 4. So for limits, do we care what we're equal to? No, we only care about what we are approaching from both sides. So if the question asked you, what is the limit as we approach 4 from the left? We would have to use the quadratic. So it's just 4 squared or 16. So the answer there is 16. If they wanted to know what the limit was from the right, we would use this function, and it would end at just before a height of 2, right? The square root of 4 is 2. So this function, the left end is heading to a height of 16. The right side is heading to a height of 2. The limit actually doesn't exist at 4 because those things don't match and line up. And that function is definitely not going to be continuous because one of the sides heads to 2, one of the sides does not. There's a little gap there, okay? So that's just some types of problems I wanted you to see where a left side limit gives you one answer, a right side limit gives you another answer, and then the limit as we approach 4 without any restrictions does not exist because of the fact that where are we going? Are we going to 16 or are we going to 2? And so that is the issue, okay? Does that make sense how that notation would work? For a piecewise function, if it's a border value, you have to be careful, okay? Now let's jump to this picture. And let's go through these limits, okay? So the first one says, we've got this function r. What is the limit as we approach 2? So here is a vertical asymptote at 2, at -3, and at 5. As we approach 2, if and only if both ends are going to the same height, can we give it an answer that is related to infinity? So that limit as x approaches 2 is just going to be a negative infinity. Many times when you approach an asymptote, it may not exist because of the fact that you have 2 different heights. Example, look what's happening at -3. The left side's going to negative infinity, the right side's going to positive infinity, okay? So now let's look at B. They want to know what is the limit as we approach 5. Are we going to the same direction from both ends? Are we going to the same direction from both ends, both sides? Yes, so what's the answer? Positive infinity, exactly. Now, the reason they split up C and D is because as we approach -3 from the left, we are going to negative infinity. As we approach -3 from the right, we are going to positive infinity. So if they ask what the limit is at -3, we would say it does not exist. So be careful with that. So that's just a little reminder of how your limits to at vertical asymptotes are going to work. So as you approach a vertical asymptote, your limit will always be positive or negative infinity. It may not exist if both sides are not going a certain direction. Let me see what your next page is.
It's the same thing.
Okay, go up to the next page after that. Is that the title? Okay. Gotcha. Okay. So skip, guys, to this page right here, where we're going to talk today about limit laws. Now, for us to continue to head toward more calculus-related topics, we have to know how limits work and how we can calculate limits for a variety of functions. Without these limit laws, we can't do eventually something called a derivative, which means we can't do something eventually called an integral. So these are super important that we understand these laws because they're going to kind of blend right into what's coming. So the limit laws basically say, so if we have two functions, one has a limit when we approach C of L, one has a limit as we approach C of M. K is just a constant. The basic thing to know here is if you have a constant inside by your function, you can take it out to the outside. That's all that part means, is if you have a constant inside, just take it out. The second one, if you have two functions added together, split them up and evaluate each one separately. Same thing with subtraction. If you have two functions subtracting, split them up and subtract. If you have two functions multiplying, split them up and multiply. Now you can do the same thing with division, but if the bottom function is approaching 0, that would be an undefined quantity. But if you're trying to divide two limits, if the functions can be evaluated separately, separate them and just divide their limits individually. And so then it makes sense because of the multiplication rule that if you have a power on a function, ignore it, take the limit, and then take that answer to a power. Now, why is that important? Well, we can get some very complicated things inside the limit, but if we know we can kind of split it apart and evaluate each individual little piece, it will make our lives easier. And feel free to abbreviate some of that. The highlighted stuff is the most important part. So just abbreviate what you need to. The main takeaway from this entire page is you can evaluate the smaller piece, and then you can then, if there's a constant, multiply by that constant. You can, because there's going to be some complicated limits that we have. And if we can kind of break them down a little bit, it will make your life a little easier. Okay. So the first, because of that, that takes us to some kind of consequential limits. If you have a limit of a constant, so like the limit as x approaches 6 of 5, what height are we approaching? 5. So it makes sense that the constant is your answer. So what is the limit as x approaches a for a linear function x? Well, it's just going to be a. So if we have the limit as x approaches 2 of x, the answer is 2. You can see it's just a direct substitution. 2 goes in for x, bam. Then because of that, remember that last power rule I was talking about is if we have a power on it, you can just evaluate the function at a and just then take it to the n power. So here's an example of that one. That's a 3, a very ugly 3. I don't think I can fix that 3. That looks a little better. So square roots can be evaluated later. Nth roots can be evaluated later. So it's just important to note these don't have to be hard if we understand that we can break them down a little bit. And I'll show you what I mean when I do some examples. And I've tried to like include an example. They've mentioned that your function would have to be positive if n is even. If it's a square root, it's only defined if you have an even function inside, or a positive function inside of an even. So let's take a look at this particular function. So the f function is in blue. There is a little hole here, but it is defined at this point right here. I'm going to highlight the x and y axis because it's kind of hard to see. So let me just kind of highlight the x and y axis for you. Okay, so let's take a look at our first one. It says, what is the limit as we approach -2 of 3 times f of x plus g of x? Now I'm going to write it a little differently using our limit laws. I'm going to do 3 times the limit as x approaches -2 of f of x plus the limit as x approaches -2 of g of x. Now, you don't necessarily have to write it like that, but that's mathematically how you're going to do it, okay? So you'll notice I've split it apart. I've taken the constant, moved it out in the front because it's just going to multiply by whatever it is. Now the f function is in red. We are approaching a height or an x value of -2. So here's x is -2 right there. Our f function, is in blue. Our g function is in red. So if we are approaching -2 on our f function, what height are we approaching? 1. So this right here is 1. Okay. So now we are approaching -2 on our g function, which is in red. What height are we approaching when x is -2 on our g function? -1. So then it just becomes 3 minus 1, or 2. So we were able to ignore the 3, find the information from our graph, then multiply by 3, and then add the 2 results together. Okay. Now let's move on to B. So we can really rewrite that as the limit as x approaches 1 of our f function times the limit as x approaches 1 of our g function. We can get those two answers and just multiply them together. So if we go over to an x value of 1, so here's an x value of 1, and if I look at my f function in blue, what height am I at? What height am I at? If my x value is 1, my height is 2, right? On my g function, when x is approaching 1, what height am I at? From one side, but see how the other side is at 1? It doesn't exist. So since that doesn't exist, the multiplication doesn't exist. So be careful with that. Now, Dylan, if it had that little -1 notation on it, if that had that little -1 notation on it, you could have said that -2 works. But because it wanted, it's that both direction sort of thing. Be careful with that. Okay, let's take a look at the last one. So this is just the limit as x approaches 3 of g divided by the limit as x approaches 3 of f. So we can evaluate or take each limit individually and see what we get. Well, if we are over here at 3, there's 3. Our g function is in red. What height are we at on our g function, or what height are we approaching? 1 from both sides. In our f function, that's in blue, what height are we approaching? We are only doing it from one side. So there are times where they will just give that one-sided limit, but technically it doesn't matter because we're approaching 0 anyway, and we can't divide by 0. So no matter which way we slice it, that one is undefined. So that's an example of a graph with the limit laws. Yes? So let's take a look. So our g function is in red. When we are at an x value of 3, that's here, the height on our g function is 1. We are coming into a height of 1 from both directions as we approach an x value of 3. So that's why that one was 1. Okay, so it should come in from both directions. Any other questions about that one? Okay. So let's think about a polynomial. Are there any holes, gaps, jumps in a polynomial? Are there any excluded values that we have to worry about? No, I can plug in whatever the heck I want. If you were to draw any of these on a sheet of graph paper, the graph would be a continuous. You never even have to lift your pencil. Now, so this one, you can just use direct substitution. Now, why can you do that? Well, because it's really just going to be the limit as x approaches 4 of 3 times x squared minus 5 times the limit as we approach 4 of x plus the limit as x approaches 4 of 7. Now, what is the limit as x approaches 4 of x? 4. I directly substitute in. It's 3 times 4 squared minus 5 times 4 plus 7. It's direct substitution into a polynomial function. So if you want a limit of a polynomial, it's great. Just plug it in. Now, you have to be careful about b. Although technically, I can do the limit of the top, and I could break it down just like I did for a, over the limit of the bottom, and I can break it down just like I did for a. But what does the bottom have to be concerned about? It can't be 0. If we plug -2 in the bottom, do we get 0? No. So it's a direct substitution example. Because in the top, we get -2 squared plus 2 times -2 minus 1 over 6 minus -2. That's 4 plus 4 minus 1 over 6 plus 2. So if you were to go into the graph, think about that graph. That graph, if you pulled it up into Desmos, the only value that is excluded is 6. If you plugged in 6, or if you scrolled across 6 on our graph, so let me show you 6 here. There's a hole in the graph. It's a very... I'm getting closer. Unless it's an asymptote, just a second. Oh, I think there's an asymptote there. Anyway, there's a problem at 6. There's not a problem at -2. So if we looked at -2, -2 is going to a height, just a sec. -2 is going to a height of 7/8 from both directions. It just is, okay? So be careful. Yeah, I know. I'm just trying to see what I did wrong. So -2, oh, here, look what I did. This would be a -4. I like Desmos because then I can check if I'm right or wrong. Please use Desmos to help you. That's a -4, which makes that a -1. Because that's -1/8. I'm like, wait, what? Why did they get -1/8? Anyway, so the height as we approach -2 is -1/8. There's no issues on the graph at that particular point. You'll see we're coming into that height from both directions. There are no issues. There's no breaks in the graph. Everything is wonderful. The only value that has an issue is 6. That's the only value right there that messes that up. 6, you mess it up. I'm sorry. Okay. Now let's get rid of that. Okay. So as long as we have a polynomial or rational function that a is in the domain of the function, then we can use direct substitution. So if f is a polynomial or a rational function and a is a member of the domain, then plug it in. Don't make it harder than it is. So the only values we're going to worry about are our rational functions excluded values because we would get a zero denominator. So you may recall last year when we started talking about domain and range, we excluded values where we had zero denominators, and we exclude them here for direct substitution. So if two functions are equal, but a is just undefined in one of them, then the limit as we approach a in both f and g will be the same thing. So if one has a hole there and one doesn't, you can use the smaller version, the better version, the nicer version. Because remember, a limit, you don't consider what's happening exactly at that point. You're looking at as the function approaches that point. So it acts like something everywhere but a. Well, let's just use the extra one. What do I mean? Well, let's look at example 4. So we've got this function that looks like this. Now, I apologize for my graphing skills, but doesn't this graph look exactly like x plus 1? Except at the point 1. At the point 1, there's a little hole, and we've colored in the wrong spot. So what this says is just follow x plus 1. So we know that the limit as x approaches 1 of g of x is the same as the limit as x approaches 1 of x plus 1. They're going to be the same thing. We know how to evaluate this limit without even the graph. We can use direct substitution. It doesn't matter that it is defined in a different location. Who cares? A limit is not what we land on, it's what we are approaching. So that's just direct substitution. So that's just 1 plus 1 or 2. Aren't we approaching a height of 2? So we are able to just use a simplified version. Now that's helpful when we have some fractions that can reduce. Let's say we have a fraction where the denominator gives us a whole. Where there's a hole, we can reduce it. We can then stick in a number and it will be okay. Because it's just a graph with one missing piece. We don't care about that missing piece if it's what we are approaching. So this is what I always say. Try direct substitution. If it works, yay. If it doesn't work, can you reduce it and then try it? If that doesn't work, you might have to look at the graph. So let's take a look at some examples. If I try direct substitution on example 5, I get 4 squared minus 16 over 0, which is 0 over 0. That tells you that I am able to find an equivalent function to that doesn't have a problem at 0. 0 over 0 tells you that you can find a better version. Because technically there's a hole in the graph. And we don't care about the hole at the graph. So let's get it simplified. Well, what algebra can you do? Well, there's some algebra hiding in this problem, right? H plus 4 can be squared. H plus 4 is just H plus 4 times H plus 4. So that's just H squared plus 8H plus 16 minus 16 over H. The 16s can cancel out. You get H squared plus 8H divided by H. And I can cancel out the H's. I get H plus 8. So that means That function up there that looks very complicated and disgusting will look exactly like h plus 8 with a hole in it. So this, our function up here, is really h plus 8 with a hole when h equals 0. Does a hole matter when we're doing limits? Sure doesn't. So because I found the nicer version, now I can just do the limit as h approaches 0 of h plus 8. Direct substitution. Just plug in 0. What's 0 plus 8? 8. So if I find the nicer version, I'm going to use the nicer version because it tells me what I'm approaching. Yes, there's a hole there. Don't care. Okay. If I can use direct substitution, I use it. Now let's look at example 6. In example 6, if I plug in 0, I get the square root of 4 minus 2 over 0. I always kind of try a direct substitution to get me started. And I get 0 over 0, which tells me that I need to mess up the algebra. I got to find a better version. I got to find the better version. Now, with 1 like 5, the better version can be found easily if you just manipulate the algebra. 6 is a little harder. If you have a square root function, write it out. On top and bottom next to it, you're always going to multiply by the conjugate. So the conjugate is the square root of t plus 4 plus 2. Remember, the conjugate just switches the sign between them. Switch the sign between them. You can't touch what's in the radical. You don't want to touch what's in the radical, but you do want to change the sign between them. Now, to find this better function, on the bottom, do not waste your time to multiply. It doesn't help you. It isn't of any benefit. Just leave that alone, okay? The only thing we want to multiply are the conjugates on top, because the conjugates on top will square the first thing. Remember, that's just a plus b times a minus b. It's just going to be the first thing squared minus the second thing squared. So it's just going to be t plus 4 minus 4, which is going to give us t over t, the square root of t plus 4 plus 2. Now, what was causing the problem in our denominator? The t. Can the t cancel out now? Yes. If you get to that point where the thing that is causing the issue can cancel out, you have found where the problem lies. You found a way to fix it. So just cancel those out. And so our new better function we get to look at is 1 times the quantity of t plus 4 plus 2. Now watch. If I try direct substitution of that new and better version, it works just fine. I get the square root of 4, which is 2, plus 2. I get 1/4. So if you get 0 over 0, there's something hiding in there that you can remove by doing some algebra. If it is a quantity like 5, manipulate the square, multiply it out. If it is a square root, use the conjugate. Now, we're going to use that conjugate idea in multiple ways, but please get in the habit. If you try for a limit and you try direct substitution and you get 0 over 0, those are the tricks you want to find. Is there a way to manipulate the algebra? Everybody good with those? There's some tricky algebra in that. So, I would, if you're doing a homework and you get to one that has a limit like that, just look at what did I do? Mrs. Hart used the conjugate. Try using the conjugate, okay? So this is just a theorem that you have to, that I've said again and again, and it basically says that the limit will only equal L if from the left and the right you're going to the same place. That's just saying the left and the right have to match. The left and the right sides have to match. There are times, we saw in that one problem, we only kind of were coming in from the left. Square root problems will sometimes only have one side. So sometimes we will define it. We will only say what is the right side and left side limits, because that's the only side we have to look at. So just, be careful how it's worded. That notation, that plus or minus, you'll need to know that's a left and right notation. That notation doesn't go anywhere. So I want to take a look at some problems that occur in some specific functions. So I want to talk about the absolute value function. Last year, when we were learning parent functions, we learned that the absolute value is technically a piecewise function. It is the opposite of x for any negatives or x for any positives. We learned that little piecewise function, okay? So here is where that piecewise function is very important in a calculus class, because let's take a look at the limit as we approach 0 from the left and from the right. Okay, now it's a piecewise function. So this is anything coming in from the left that's less than 0. So if you plug in 0 to negative x, what do you get? If you plug in direct substitution, the opposite of 0 is 0. Now this is what we use when we're coming in from the right. So, and remember, a piecewise function could have problems at the border. The border 0. They're asking about 0. So as we come in from the right, if we plug into regular x and we plug in 0, what do we get? Since they match, then the limit as x approaches 0 must equal 0. If they didn't match, then the limit wouldn't exist. But because they match from both the left and the right side, you're good to go. Now here's the one that doesn't quite live up to what we want. Okay. So let's look at it how example 8 is different. We're still approaching 0. We've got an absolute value, but we got an absolute value over x. Okay. So an absolute value over x, I'm going to call this g of x. So it's going to be negative x over x when x is less than 0, and positive x over x when x is greater than or equal to 0. What does negative x over x reduce down to? What does negative x over x reduce down to? Negative 1. What does positive x over x reduce down to? 1. So remember that Heaviside function we looked at where we were at 1 or 0? This is having this similar type effect. Something weird is happening. Okay, so let's approach it from the left. Let's approach it from the right. Let's see what we get. If we approach 0 from the left, what height are we coming into? Negative 1. If we approach 0 from the right, what height are we coming from? 1. Do they match? No, don't match. So the limit as x approaches 0 does not exist because we're coming in from different directions. And it's all about the fact that our absolute value function is a piecewise function, that that switchover from negatives to positive can cause an issue. Now, if your absolute value is just an x, that happens at 0. If your absolute value is like an x plus 1, you might have to find, that's going to happen at -1. There might be a switchover in a different spot. So just watch that absolute values are a piecewise function. You have to evaluate both pieces. It could cause an issue. Okay, so there's example 7 and 8. Yeah. We're going to stop here. We are going to finish this tomorrow. There you go.